just so we are going to keep thinking about grand canonical ensemble today. I'm going to talk about how fluctuations in numbers happen in the grand canonical ensemble. Okay, we will derive that relation, and it's going to be a bunch of algebra, but it's very important. And when you come to the Blackboard today, that's the type of stuff you would be doing. So this is the type of algebra that shows up in StatMech a lot. So we will be deriving fluctuations in grand canonical ensemble today. I already told you the relation. The qualitative relation that we get is that fluctuations become irrelevant as the system size increases. This is true for all StatMech ensembles at equilibrium. If fluctuations are not dying, even if you increase the system size relative to the mean, then generally speaking, your system is out of equilibrium. Something is going on, right? You have not reached equilibrium. It's a driven system. There is something is pumping energy into it. Something else is going on, right? So if fluctuations don't die relative to the mean, so we saw, for example, just to remind you, in canonical ensemble, that standard deviation of E by mean of E went as 1 over square root of n as n tends to infinity. That's what I mean by fluctuations dying. And this really follows from central limit theorem. What does central limit theorem say? Central limit theorem says if you have a bunch of random variables coming from whatever probability distribution, if you sum them up and look at their mean, it's going to behave like a Gaussian. Does not matter how you got these random variables. And for a Gaussian, this property holds true. That's where it comes from, okay? So if the random variables are not independent, then central limit theorem will not hold true, things like that, okay? So today what we are going to do is to show that for a grand canonical ensemble, standard deviation of n divided by mean of n also goes as 1 over square root of n as n tends to infinity. So last time we showed that the average of n in grand canonical ensemble is 1 over beta partial ln z, where z is now a function of mu vt by partial mu at constant v and t, or constant v and beta. Okay, we derived this last time, and I made this general comment about how partition function is generally useless. Log of partition function gives you some state function. Derivative of log of partition function with respect to something else gives you average of a state function. And the second derivative gives you the fluctuation of the state function, okay, of some state function. So this we showed last time. Today, what we are going to do is to think about sigma n square, which is the variance in n, right? How do we define the variance? Variance is defined as average of n square minus square of average. Okay. So let's get started. Number one, let's put this as equation number in my notes, it is numbered equation 0. So I'll call it equation 0. Okay, we can start anywhere. So, and this one we are going to call equation number 1. Somewhere I have an equation -1. I don't know where it is. Can't find it. We'll ignore that. Okay. So what do we want to do? We want to calculate first thing for this equation 1. It has 2 parts, right? So the second part, which is average of n squared, we can get from using equation 0, right? It's the first part that we need to worry about now, how to get average of n squared. So what is average of n squared? That is going to be just like we did last time. Go to every microstate, look at the probability of that microstate, and look at the variable that you're trying to average out. In this case, n nu square, right? When we did average n, we did p nu n nu. This equation applies for any ensemble, right? This is just probability. The choice of ensemble will change the definition of p nu. If it was microcanonical ensemble, what would happen? P nu would be constant, right? It would just come out. And what would be the average of n square? It would be n square itself. It's not fluctuating. In a microcanonical ensemble, you're working with N, V, and E. In a canonical ensemble also, P nu now depends on nu, but not on N. It does not depend on N nu. So you can again pull it out, right? And you're again left with N squared. Here, it's going to be painful. So here, we will use, oh, now I remember equation -1. Equation -1 is P nu is equal to 1 over Z e to the power minus beta E nu minus mu N nu. Okay, we call this equation -1. We are going to use this one over here. So this becomes summation nu N nu square e to the power minus beta E nu minus mu N nu by, sorry, the whole thing divided by Z. Okay. So let's keep going. Let's write it down explicitly. So N square is now, and all I'm going to do next is algebra, just manipulating terms. So I put the Z outside. I take the Z outside the summation because it does not depend on nu. I have summation nu now. Then I have a N nu square multiplied by 2 exponentials. So for the first one is e to the power minus beta E nu. The second one is e to the power plus beta mu N nu. Okay, so now what I'm going to do is to again, just some more algebra, and I will move terms around. So I will write this as 1 over Z summation nu, and one of the N nu I'm going to bring over here. Okay, so I will leave the first N nu over here. The second N nu I will take further to the right. This multiplied by e to the power minus beta E nu multiplied by N nu, the N nu that I borrowed from the left, but not just N nu, I will write it as beta N nu divided by beta. So I have multiplied divided by beta, okay? Multiplied by e to the power plus beta mu N nu. So the beta that we have over here does not depend on nu, right? Beta is just a number in this case, which is forced on the system. So beta can be brought outside, and this thing becomes 1 over beta Z summation nu N nu e to the power minus beta E nu multiplied by this stuff. That is just like k e to the power plus kx. Remember, we had the same term last time, and start recognizing things like this. When you have exponential with one thing, one part of the exponential up front. So what does this mean? This means we could have gotten this by writing down partial derivative of e to the power plus beta mu N nu with respect to all the term except beta N nu. So that will be partial with respect to mu. Okay, I will leave this for just a moment. Any questions about this? So what do we have now? Let me write down this equation on the next page. So I just showed that N square is equal to 1 over beta Z summation nu N nu e to the power minus beta E nu partial of e to the power plus beta E mu N nu with respect to mu. Okay. Now I realize that, well, this thing does not depend on mu. This is something you need to keep developing intuition on. Every once in a while, I say this thing depends on this thing does not depend on that. In this case, what are my control variables? My control variables are beta, mu, and volume, right? That's the ensemble I'm working with. And this thing does not depend on volume. It depends on beta. It does not depend on mu, right? So if it does not depend on mu, I can put it inside over here. I can bring it back inside. Then this will become 1 over beta z summation nu n nu partial with respect to mu of e to the power minus beta e nu minus mu n nu. What can we do now? We are not mathematicians, so we can move our differentials wherever we want. If we were mathematicians, we would be very nervous about things like that, especially when we do integration later. Later, we will swap our order of integration anytime we want because we are not mathematicians, who cares? So we can bring this partial with respect to mu outside, right? It can just act on the whole thing. This is a subtle one. You would be like, well, how about n nu? N nu does not depend on mu, right? N and mu are conjugate variables. They are connected, but they're different, okay? Mu is something you imposed on the system. What is the chemical potential? And nu changes in every microstate. So mu can be brought out, and this becomes 1 over beta z partial with respect to mu of summation nu n nu e to the power minus beta e nu minus mu n nu. Oh, we are getting somewhere. This term inside the square bracket, can we do something to it? What does it look like? Trevor, what do you think?
It should look like equation.
Like the average of n.
Yeah.
But it's missing something.
Not divided by z.
The partition function is missing, right? So how do we divide by z? By multiplying by z, right? So we do a z over here and a z over here. Now this is the probability. This is equation -1, right? P nu is equal to that thing. And what do we have? Suddenly we have average n square is equal to 1 over beta z partial with respect to mu of z n bar. Okay, let's call this equation 2. Who here is tempted to cancel out the z? Julia is tempted. Why should Julia not be tempted? Why should Julia resist this temptation? Samyak, what do you think? Or Julia, do you have an answer? First, let's give you a chance.
I mean, I guess we can't just take it out of the
No, because what does z depend on? Mu. It's a function of mu, right? So would you agree, Samyak? It's a function of mu. Z depends on mu. So we cannot just say like, oh, bring it out. And you will make mistakes like this when you get desperate and the time is running out. You'll be like, oh, let's just cancel it. It looks the same. Often I get StatMech answers where people start from one end, they start from the other end, and somewhere in the middle, there is a gross approximation. And if I'm not careful in understanding it, I won't even catch it. You do things like this. You just cancel out and it looks okay. Now we can't cancel it out. We have to suffer through it. So what we are going to do now, we will write down, we will use product rule. So average of n square is 1 over beta z, z multiplied by partial n bar with partial mu, plus n bar multiplied by partial z by partial mu. Okay, so average n square. Now we can cancel this z out, right? In the first term, the z has come out of the differential. So we can do that. So that will become 1 over beta partial n bar by partial mu. And in this case, we can write it down as n bar over beta partial ln z by partial mu. Okay. Have we seen this thing before? We took the log of a partition function and we differentiated it with respect to an intensive parameter. So it should correspond to the average of something. Which thing? N bar. That is N bar, right? Soon you will be on Blackboard proving this. Doesn't look very promising. So that's N bar. I hope you see it as clearly as I do. It's well related to. So we've seen that N bar is equal to 1 over beta partial ln z by partial mu. So actually, this thing is n bar, right? So what do we get? We get n bar square. That's interesting. We are getting somewhere. This thing is now equal to 1 over beta partial n bar by partial mu plus n bar whole square. All of a sudden, our variance just appeared out of nowhere. That's crazy, right? Because what was variance? Variance was average of squared minus square of average. In other words, we have just shown that variance of n is equal to 1 over beta partial n bar by partial mu. This we call as equation 5. And this is all we wanted to show. This is the expression for variance of n. I earlier said that variance and fluctuations are second derivatives of the partition function, of log of the partition function. This looks like a first derivative. How do I get a second derivative from this? I have to put the expression for n bar, right? So I can go one step further. Let me write down this equation again on the next page. Equation 5 was variance of n is equal to 1 over beta partial n bar by partial mu. But I know that n bar is equal to 1 over beta partial ln z by partial mu. So in other words, this becomes 1 variance of n is equal to 1 over beta square what should I do now? So, well, firstly, let's not be too speedy. Partial by partial mu of n bar. What is n bar? N bar is 1 over beta partial ln z by partial mu, right? Now this beta can come outside, and this becomes 1 over beta square, double derivative of log z with respect to mu. So we again get that relation that variance n is second derivative of log z with respect to chemical potential. Should I tell you one problem I'm going to give on the midterm? Great. Midterm, one of the many gazillion problems you will have. It's basically noise. You will prove on the midterm that variance of n is actually related to average n square by beta multiplied by volume multiplied by kappa, where kappa is isothermal compressibility. Compressibility, what does compressibility mean? Compressibility means how much pressure do you need to apply to change the volume of something per unit volume, right? So compressibility is defined as minus 1 over V partial V by partial P at constant NT. Okay, you're going to prove this on the midterm. So go and do it today. You already have one problem done. This is kind of amazing. Remember, because variance of E for canonical ensemble, that was related to a material property. Remember which property? Heat capacity. And variance of N is related to compressibility. So it's again an example of a fluctuation dissipation theorem. How do you measure compressibility of something? How would I measure compressibility of DD? I'll try to compress him and see how much resistance he's applying, right? It won't be an equilibrium process. It will be a terrible process. DD won't like it. But here you're saying, don't worry about that. Just study a grand canonical ensemble at equilibrium. See how the number of particles fluctuate and just measure this fluctuation. And that will tell you about the compressibility. Later on, this is related to something called fluctuation dissipation theorem, and particularly something known as linear response theory. When you apply small perturbations to system, the response is kind of linear. And that's where it all comes from. If you take Chris's class 2 years from now, you will study these things. So I want to make a point here again that the big picture is that fluctuations of energy were related to the heat capacity, and maybe I will put this on the midterm, maybe not. We showed sigma E square for canonical ensemble, right? We did not show it for grand canonical ensemble. Remember, we have not calculated sigma E squared for grand canonical. We would have to do the same thing, average of E squared minus square of average. We haven't done that. So I want you to check or think about this. does this apply to grand canonical ensemble? Is it the same relation or something changes? Maybe this will be on the midterm, maybe not. But generally speaking, we have seen that sigma E square, turns out it is related. The prefactors might change, so think about that. Sigma E square is proportional to CV. The fluctuations in energy tell you about heat capacity, and fluctuations in number tell you about isothermal compressibility. Any questions? I'll pause for a moment. Just think about it and ask me if there are any questions. I don't want to go too fast. Doge. Too much bloat. We removed them. You can mark any of them. Does it matter? It does not matter.
I thought I might have missed it.
You're paying attention. Good job, Ami. Okay. So there are two books that people use in StatMech for chemistry. One is Chandler. I like this one because it's very tiny. When I was a postdoc in New York, I could just put it in my down jacket and read it on the subway. It's great. This you cannot put on in your down jacket. It's too heavy. The Macquarie's book, a lot of people also use. And if you open first chapter in Macquarie, and you can find the PDF online, you don't need to buy it. This one I do recommend buying. Okay, this is a mandatory book, and it's good to have it. If you open Macquarie's book, the first chapter is classical mechanics. The second chapter is canonical ensemble. And Macquarie does not derive canonical ensemble the same way that Chandler does. Okay, it's very different. Macquarie also talks about most probable distribution and equal a priori probabilities and things like that. But then he goes on a tangent. He takes a different view. How did we derive our ensembles in Chandler? In Chandler or in this course, we thought about, again, the fully isolated system ensemble, right? And then we thought when an ensemble exchanges something, we are just going to embed in a much bigger environment, right? And the full thing is always fully isolated, right? And then we did Taylor series. This was the philosophical approach that we took here. Macquarie does not do that. Macquarie introduces a formula for entropy, which is known as Gibbs entropy. And then he derives everything by doing something known as maximum entropy framework. So it's a different way of deriving StatMech. And I'm going to tell you about Gibbs entropy today. And if you have time, especially over spring break or things like that, you can read it, how to derive things like that. We have only one undergrad in the class. When you take your StatMech in grad school, for example, you might be like, I know ensembles, and the professor, if they follow Macquarie, they will derive it from a completely different way. And the idea there is to maximize entropy by adding constraints. So in physics, this is known as maximum entropy framework. So if you have a canonical ensemble, your constraints are, you know something about the average number of particles. If you have you know something about the average energy, right? If you have a grand canonical ensemble, you know something about average number of particles and average energy. So you always maximize this entropy plus constraints that you have. And that's how Macquarie solves everything. The answers that you get are the same. The probability, what matters in the end is P nu, right? Probability of a microstate, that you get the same. What's the advantage of this approach over Chandler approach? The advantage is that when we tried to, there was a very funky derivation that I did last two times, which is when I tried to think about how does A connect to log of Q. Remember? I assumed microcanonical. For example, we were talking about this. We assumed microcanonical when I wanted, then I assumed canonical when I wanted, right? It was a very bizarre derivation. In this case, that part follows out nicely. You don't have to assume that thing. This connection with thermodynamics falls out nicely. But the cost is you have to know the expression for Gibbs entropy. We have to know what is this entropy formula. And where did that come from? That Macquarie leaves as as an approximation, right? So for that reason, in Maryland, we prefer the Chandler approach of deriving ensembles. It's almost the Maryland school of thought. Most places don't. Maryland and Berkeley, David Chandler himself, of course, used to teach it this way, but a lot of places, it's a bit philosophical. You have to think about what exactly happened and you have to go through it carefully. This McQuarrie approach, people even do in PChem, in undergrad. It's very mathematical, blah, 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 you're done. But all of that happens if you assume the Gibbs entropy formula, otherwise it's not going to happen. So now, but I do want you to know what is Gibbs entropy, so I will cover that part. And this also connects to Shannon entropy in information theory. Shannon was an electrical engineer or so, something like that at MIT, I think, or Bell Labs, was it Bell Labs or MIT? I think Bell Labs in early 1950s. And he's really the father of information theory. Like computers and internet, nothing would exist unless people like Shannon and another guy named as John von Neumann were not there. So these people did fundamental work. We are not going to talk about Shannon. We will talk about Gibbs today. And the entropy that we have studied so far, that is Boltzmann entropy, right? So the formulation we have studied so far we gave it a name, we call it Boltzmann entropy. How do we define Boltzmann entropy? Boltzmann entropy is defined as S is equal to KB ln omega for a microcanonical ensemble, right? This is the definition of Boltzmann entropy, which is what we used. So we didn't prove this, remember? We just threw it out there. We said if omega is the number of microstates of a microcanonical ensemble, let's define entropy as log omega. And we showed it has nice properties. Number one, it is extensive. If you bring two independent systems together, omega 1 multiplied by omega 2 gives you log of omega 1 plus log of omega 2, right? So this is in anything you have to start with some assumptions, right? Even in pure math, you have to assume real numbers exist. You can't start. You have to have some axioms. And these are the axioms in our StatMech is we say, this is our formula for entropy. McQuarrie does not do that. McQuarrie starts with Gibbs entropy and then he goes from there, okay? So this was our microcanonical ensemble and we assumed that system plus bath is equal to environment, right? And that's how we started for every system. And we assumed that system is much smaller than bath. That's how we got going. So what I'm going to do next is to call this as S naught, okay? And this as omega naught, where the naught 0 denotes system plus bath together, the full sum, okay? S naught is system plus bath. So you have a system, you have a bath, together they are microcanonical ensemble. So now let's say that the system is in some microstate nu. If the system is in some microstate nu, then S naught should be equal to S nu of system plus S nu of bath. Why do I say bath nu? Because the entropy of the bath depends on what is the microstate of the system, right? That's how we calculate the number of states. Or S nu system is equal to S naught minus S nu bath. Okay. What is S naught? S naught I wrote down in equation number 6. Oh, I got it correct. Ami is happy. Ami is gonna be angry later, so let me call it 3 and 4. Happy, Ami? Great. You'll be like, where did those equations go? Doge. So S nu bath, and so what do we have S naught? S naught is KB ln omega naught. What is S nu bath? We calculated S nu bath when deriving our ensembles. S nu bath is ln omega. If you fix the energy of if you force the system to be in a certain microstate, then for given that microstate, the remaining stuff, the bath, is a microcanonical ensemble. This was sort of the abstract thing that we assumed while deriving, right? The bath is not a microcanonical ensemble in general because it is exchanging energy and things like that, right? It's exchanging number. But if you fix the system in some microstate, then the bath is also fixed to be in certain energy and number, right? Because the total is n, and you are saying the system has nu and e nu, then the bath must have n minus nu and e minus nu, right? So we can use the microcanonical formula for that particular setup. It will be e minus e nu, omega of e minus e nu, and n minus n nu. So we can combine these two and write them as S naught minus S nu bath is equal to minus KB ln omega E minus E nu n minus n nu, omega depending on these two things, divided by omega naught. The thing that I just put in a circle, have we seen that before? Does it have a name? This is some of the abstract part of the course we have done so far. So it's because we use it only when connecting to thermodynamics. But if you remember, if anyone remembers, I will be very impressed because I forget what is this.
That's the probability of obtaining that micro.
Correct. It's P nu. Does everyone see that? This is what we did, right? We made a table, remember, counted number of states and said P nu is that number of state divided by everything else. So this is P nu. So this is minus KB ln P nu. Okay, we use this while deriving connections between canonical and thermo, grand canonical and thermo. Great. Now we are going to do something interesting. This is S naught minus S nu bath, let's call this equation 7, for a given microstate, right? Now I ask you, well, I'm not interested in a given microstate. I am interested in, let me write down the equation 7 on next page again. I'll work from there, it's page number 4. So page number 5, equation 7 says that S nu system, which is the same as S naught minus S nu bath, is equal to minus KB ln P nu, right? But this is the entropy when the system is in a given microstate. What I want to do now is to calculate the average of this entropy, averaging over all microstates, just like did for just like we calculated average of n, average of E, and things like that. So this will be average of S naught minus average of S nu bath, right? Or it will be average of S naught minus S nu bath together, correct? Just algebra. Now, remember, how do we calculate average of anything in StatMech? Same formula, we go to any microstate. We take the probability of that microstate. We don't know which ensemble we are in. And we look at the random variable that we are trying to average, S naught minus S nu bath. But now, equation 7 has given us an expression for S naught minus S nu bath. We can put that over here. Use equation 7 in above. And what do we get? We get S nu system averaged is equal to minus KB all microstates P nu ln P nu. Or instead of writing averaging the entropy over all microstates, that is the observable entropy, that is the thermodynamic entropy. And this is what we call Gibbs entropy. S Gibbs is minus KB going to every microstate and doing P log P. You can show, maybe I will give it in the homework after the midterm, that this is consistent with Boltzmann entropy, that it follows all nice behaviors. Chandler just gives it an exercise problem. So first you will have to think, what do you mean by consistency? Then you can prove it. So Macquarie's book derives everything by starting from this formula. It just takes it to be a given. And people still argue over this. There are some people who think that Gibbs entropy and Boltzmann entropy are not always equivalent. Generally, when the equivalence fails, it's because you're not in equilibrium. That's the general reason for most things in thermodynamics. But in information theory, in computer science, in machine learning, this entropy formula is everywhere. It's used to train machine learning models all the time. People use these things invariably. People don't think about our poor S is equal to K log omega formula, but this one is actually one of the most heavily used formula in the world currently, without doubt. Okay. Any questions about this? All right, now we're going to go to the blackboard. Hey, Noah, I'm going to stop recording. This part is going to get so you can stay on Zoom. I don't know what you're going to do. I'm not going to ask you to come to the blackboard, but I'm remembering this is, by the way, you have been on Zoom 3 times. For the 4th time, I need some explanation, like some proof or something from you. Okay.
Oh yeah, I'm sorry. I've still been sick, and I didn't want to
Yeah.
come
So
to
don't.
class.
I mean, if you just don't show up for the 4th time, also, then all these people sitting over here will be like, why should we show up, right? So I've kept this. I don't expect any reasons if you don't show up once. Okay, it's fine.
I'll be back next week.
No, this is not for you. This is for everyone. If you're not coming 2 times in a row, please have the courtesy of telling me what happened. If you're not coming 3 or 4 times in a row, then something is serious. Let's have a chat. What's going on? And you don't have to tell me private details of any sort, but I just don't want the thing to get the policy to be exploited. On 13th of March, for example, I will be in Switzerland, so I will be teaching from the Alps on Zoom after giving my talk. Okay, so I'm going to stop recording. I will just keep Zoom on. I mean, you will hear things. You won't see things. What do I do? I do stop recording.